All right, we're rolling.
24 out of 4 now.
Questions?
On that, you said 7. Okay, I'm really confused on how to do 8 and 9.
I have my own copy today.
All right. So when you're dealing with orbit, in the ideal circular orbit, that I know there's a gravitational pull here. If we're talking really ideal, then the sun is at rest. This is being pulled inwards, and because that's perpendicular to the motion, that it's going to travel at a constant speed, changing directions. So that is the force due to gravity, and then my velocity is in that direction at that point. And my recollection is that we worked through at least the basics of setting it up in the Newton's second law. That F equals ma, big G, mass of planet, mass of sun over r squared is equal to mass times centripetal acceleration, e squared over r. So now a circle would be an ellipse of eccentricity equals 1. So when I say eccentricity less than 1, that means it's now getting squished. Because in reality, planets actually don't travel in a circle. So I got sun, and exaggerating it, that's horrible. If I draw this first. And so the sun is not exactly centered there. So when the planet is here, what is the force acting on it?
Gravity.
Let's more
Fixed gravity.
Thank you. All right. And it's directed right at the sun. The velocity is tangent to the curve. So the velocity is in that direction, and they're no longer perpendicular. Which means that some of the force is in the direction of motion, and some of it's perpendicular to the direction of motion. The part that's perpendicular to the direction of motion is going to cause a change in direction. The part that is parallel to the direction of motion is going to cause a change in speed. So as the planet is traveling this way, will it speed up or slow down?
Speed up.
All right, what about when it's here?
Slow down.
Yeah. And that's what it does. The planet basically speeds up as it goes whipping around the sun, and then slows down, and then starts speeding up again and slowing down, and so forth. I mean, that's the general background for problem number 8.
On what? On what?
On Master Set 7. That was not an energy answer, but it still works. Yeah. Well, actually, just think later from an energy point of view. What are the 2 types of energy?
Force gravity. Oh,
Two
kinetic
types.
and potential.
All right, and get ready.
Rest.
Oh, yes. What's the formula for kinetic energy?
1/2 mc squared.
That was not everybody. Don't worry, I'll ask you later on. So that's kinetic plus potential. So that's 1/2 mv squared plus, what's the formula for potential energy?
Which one?
The one associated with the generalized gravitational force.
It's m1 m2 over r.
Is the first thing you said G?
Big G.
Yeah, okay, big G, you missed something.
It's negative.
Yes, it is negative. So this would be mass of the planet in this case, so this would be mass of the planet, mass of the sun, over
R. Why is it negative?
Well, I guess conceptually it's negative because as things go, well, think about the classic gravitational potential energy, where G is relative, little g is relatively constant, mgh. So this is gravitational potential energy if G is relatively constant. This is gravitational potential energy if little g is not constant. So I take an object, I throw it up into the air. It starts out with kinetic energy after it's left my hand. It slows down so that kinetic is getting converted to potential energy. Because the only force acting on it after it leaves my hand is the gravitational force, which is conservative, so energy is transferred from one form to another. So that kinetic becomes potential. So as it gets farther away from the Earth, its potential energy will decrease. Sorry, kinetic energy decreases, potential energy increases. Here, if I just said G mass planet mass sun over R, as R gets bigger, so you get farther away, then my potential energy would be getting smaller. As the denominator, a fraction here, as my denominator gets bigger, the fraction gets smaller. So that would sort of be counter to at least our other experience of potential energy, that potential energy increases the farther you get away from it. However, if it's negative, it becomes less negative. It might go, so if it were positive, it might go from 100 to 10 to 5 units. Obviously getting smaller, but if it's negative, it goes from negative 100 to negative 10 to negative 5. It's increasing. So potential energy increases the farther you get away. And ultimately it comes down to math. I don't know if that worked for you or not.
Mostly.
Mostly? You've had calculus, right?
Yeah.
All right, 30 seconds aside. I've got some planet here, I have an object that's moving away. It has this gravitational pull, Fg. I know that the work, the conservative work is equal to the negative change in potential energy. And work is the integral of f dot dx. So going from some initial radius to some final radius. F is pointing that way as it's moving that way, so my dot product is going to be negative. Mass 1, mass 2 over r squared dr. dr is going away from it, from some initial radius to some final radius. And you end up with G mass 1, mass 2 over R. Will cancel out. So G mass 1, mass 2 over R final minus G mass 1, mass 2 over R initial. And that's equal to the change in the negative change in potential energy, which is negative of U final minus U initial, which is negative U final plus U initial. So doing a parallel there, well, if the potential energy is G mass 1, negative G mass 1, mass 2 over R, it works. 30 seconds aside. Probably longer than 30 seconds. Somebody tells me you're still not satisfied.
I think that made it a little more sense than the first one. I'm mostly satisfied. I don't think it matters that much. I just know you have to subtract it. It's negative.
or you add the negative, either way.
Yeah.
Do recognize though that there's more than one solution, and this should be very quick if you follow the videos. What is another solution here that would work?
R equals 0, set the usual, or infinity, wasn't it?
Now, not establishing where R is equal to 0. Well, I guess you could make an argument for this. If I know that x minus y, or say x1 minus x2 is equal to 7 minus 3. What is the value of x1 and x2 that would work?
7 and 3.
Okay, what's another?
9 and 5.
What did you do to the original solution?
I added 2 to both.
Yeah. So what's another solution that would work here, where I've got negative u final plus u initial is equal to this?
Multiply everything by 2, maybe?
Not multiplying by 2, that would give you twice the answer.
Divided by 2.
Not dividing by 2 either.
Adding something to each one.
Yeah. As long as if x1 is 7 and x2 is 3, that's a true statement. Or 9 and 5 also works if I just add 2 to the original problem. Or I can add 3 to the original problem and get 6 and 10. It still works. So any of the potential energy formulas, not just this one, any of the potential energy formulas, you get that generic equation that textbooks like to print, plus some constant. I can always add a constant to any of them, which, connecting back earlier, allows you to establish where do you want to make the potential energy equal to 0. So for an object that falls, let's say it starts out 30 meters from the ground and ends up 20 meters from the ground. How fast is it going when it is? Try that again. Starts 30 meters from the ground. It falls till it is 20 meters from the ground. And this marker sucks. I can do conservation of energy to solve this, because if it's falling, the only force acting on it is a conservative force, the force due to gravity. But where do you want to make the potential energy equal to 0? Which is over and up. Where do you want to make the potential energy equal to 0?
20 meters.
So if we make that is where the potential energy is equal to 0. And the reasoning is, because Ethan said so, then I know my initial energy equals my final energy, because energy is conserved here. And that's my initial kinetic plus my initial potential is equal to my final kinetic plus my final potential, which is 1/2 mv squared plus m initial plus mdh initial is equal to 1/2 mv final squared. And I apologize for not giving you a chance to tell me that it's 1/2 mv squared. Well, this is going to be true regardless of what Ethan says, but at this point, if we establish the final position to be 0, my initial, if we drop it, my initial is 0. We're left with GH initial is equal to 1/2 V final squared. So if we're establishing that as 0, in other words, where height is 0, what is my initial height?
10 meters.
Yep. So let's put this on a magical planet where G is equal to 10 meters per second squared. So I get 10 meters per second squared times 10 meters is 1/2 V V final squared, so V final would be 14.1 meters per second. If instead you want to make the ground equal to 0, marginally better. What changes is this. My final height is 20. My initial height is 30. Math still cancels out. So I'm left with G times 30, G times 20, and then 1/2 V final squared. If I subtract this from both sides, I end up with 10 times G, which is what we had before. Because what's really important is the change in potential energy, not the actual value itself. I stumped a number of students years ago, not planning to stump them, but just wanted to see if they understood this concept, where I gave them basically this electrical distribution. It would have been a 152 question. And I said, if the potential energy at the surface of this charged object is 0, what assumption did we make? And I got all sorts of answers, but I don't think anyone actually got it right. The assumption was that that's where it equals 0. I can establish 0 anywhere I want. Maybe the wording was to justify how the potential energy could be 0 there. And so the fact that I can make potential energy 0 anywhere I want. All right. So I think that basically addresses number 9 as well. Because if you move to a higher orbit, what's going to happen to your speed? So you're going to increase potential and kinetic energy?
This is master setting.
If the only force now we'll bring in the thruster in just a second. If the only force acting on an object is a conservative force, like the force due to gravity, if potential energy goes up, what happens to kinetic energy?
It goes down.
And vice versa. So in this particular case, I make the comment they are going to move to a higher orbit, but I do talk about the fact that there's a thruster, but it's a very short burst. There's not going to be a significant change in kinetic energy by the thruster. So the idea is that
it would lose speed because it's farther away from what's orbiting the Earth.
Yeah.
So it's farther away from Earth, so it would lose speed because it has less kinetic energy.
Yes. Well, because, yeah, I think you're there. The wording was a little bit off just at the end, but you said it loses speed because it loses kinetic energy. I think there's a cause and effect issue there.
It loses kinetic energy because it loses speed.
Because it gains potential energy, therefore it loses kinetic energy, and that means it loses speed.
It's not a cause and effect. Losing kinetic energy is losing speed. It doesn't, one doesn't cause it.
It's either losing speed or losing mass. Other questions?
Not really towards physics, but I was wondering if we could have a break sometime today, because I need to talk to you, and right after this class I have biology.
Good. Other questions?
So you said we have 4 test grades in this class. What's the schedule for the next 2 weeks of this class? All
right, the multiple choice test in essence, we've covered all the material for it. Typically for the multiple choice tests, I wait till after the test corrections for the second test are done. Because basically it's a review for the multiple choice test. And then the last day of class would be the last test on whatever material.
When would we get our test back from yesterday?
Tuesday.
Can we do number 9 from the test for the one about, the box on the bank road?
Okay.
Yeah, that was true.
Everyone here took it, right? Trying to remember the specifics of it.
It was like, there was theta and I think a 24 point something degree.
24.09 degrees is what my memory has.
Yeah. And I thought there was theta in there somewhere. Yeah.
Let's see, it was frictionless to start with.
100-meter radius.
Okay.
It was frictionless to start with, yeah.
What's the last thing?
It was frictionless to start with, yeah, that's correct.
It was.
It was frictionless in part A, friction in part B.
Okay. You had a question about both parts?
Mostly B, but also both parts really.
All right. So we look at the forces acting on it. Normal force and weight, that's it. Going down the steps. What's the direction of acceleration?
To the right.
So therefore, what are we breaking up?
Y.
Yep. So y gets broken up into its components. And so this is y sine theta, y cosine theta, weight. That's the decomposition. Now, equations of motion.
If up is positive, then Y